My name is Pierre-Majorique Léger, Co-director at Tech3Lab, and today our goal is to demonstrate the process of collecting electrodermal activity in a human-computer interaction setup. Today we'll be discussing how to record electrodermal activity, or EDA, a measure we collect in nearly every data collection session that we run here at Tech3Lab. EDA is a slow signal, and it's highly sensitive and incredibly diagnostic in HCI research. It is relatively straightforward for any researcher, including beginner, to work with. So the video is here to provide you with know-how how to collect and handle the data correctly for research purpose. So in this video, we'll go through over the essential details of setting up the sensor, running the data collection process, and ensuring that the data is reliable for analysis. We will focus on two types of data collection to start with. First, we'll run a continuous stimuli. In other words, a stimuli for which there's no specific markers, and we will need to add those markers manually. For this, we'll be using a YouTube video to demonstrate this, and we'll record EDA while watching a series of different video clips within the same video on YouTube. So we will call that a continuous stimuli. Then we'll run a multi-trial experiment. We'll show you how to conduct an experiment with very short video clips for which we will have specific markers of beginning and end. And with those clips, we'll be able to record also some behavioral measure after each clips. So these are two different examples that will give you kind of an introduction idea of how to measure EDA in an HCI context. And we'll use a video because it's a much simpler experiment, but we could also use a web-based interaction to run the same example. So by the end of this video tutorial, you should have a solid understanding how to record and work with electrodermal activity in your experiment using these two practical examples. So before we start, let's define some concepts. Let's talk about skin conductance. So skin conductance, which is one type of electrodermal activity, which measures how well the skin conducts electricity. So skin conductance is linked to the activity of sweat glands that, for example, you have in the palm of your hands, which release an electrolyte solution. To measure skin conductance, a small voltage is applied across two electrodes, resulting in a current that flows that we can record. The stronger the current, the higher the skin conductance. And we measure in microsiemens, which is the inverse of kiloohm. Typically, we collect skin conductance data from the palm of the hand of a participant, and we will use the non-dominant hand so that we can have the participant use their dominant hand to interact with the computer mouse, for example. So the area in the palm of the hand is called the Voltar surfaces. And these are unique because the sweat production is linked directly to mental and emotional process and not to temperature regulation. Signal from the brain cause the release of acetylcholine, which activate the sweat glands. This process is very different from most other functions of the sympathetic nervous system, which typically involve adrenaline. In our lab, we measure several physiological signals at once during an experiment, but for this training, we'll focus only on skin conductance. So today we'll be using a cobalt blue box to measure the skin conductance. This device was developed here internally at Tech3Lab, and we're using it in almost every data collection, and there is one blue box in every data collection room that we have here at Tech3Lab. I won't go into the detail of the instrument today, and there's a user guide that you can refer to, but it operates in a very similar way than other systems in the market, such as the BioPack, which we also have at Tech3Lab. Our setup also allows us to synchronize the skin conductance measurement with other experimental events, such as when the stimuli is presented to the participant. In our continuous recording, we'll have to insert manually this marker, and there are other ways using experimental timeline where we are able to inherit some metadata coming from the stimuli to create those markers. We'll come back to that during the video. So how do we prepare for skin conductance recording? Well, you will see in the video that we'll be placing electrodes in the palm of the hand of the participant. And before that, typically we'll try to make sure that the recording with the electrodes is optimal, and we'll use a small alcohol tab to watch the hand of the participant. We are using disposable electrode at the lab, which will be placed on the tenar and the hypotenars area of the non-dominant hand. This will ensure that the dominant hand is free for the task, like using the computer mouse. Once the electrodes are attached, we typically add a thin glove to help keep the sensor securely in place. How does the measurement works? Well, a small voltage, usually about 0.5 volt, is applied across those two electrodes. The current will flow between them, which is proportional to the skin conductance, and it is recorded as a continuous signal. In the recording we'll do today, we'll have a sampling rate of 100 Hertz. So that means we will have a measurement of the skin conductance 100 times per second. The signal is then amplified, filtered, digitalized, and stored on for analysis. It is actually stored on the micro SD card that will be found inside the cobalt blue box. So there are different types of skin conductance measurement. Skin conductance data can be categorized into the tonic and the phasic measurement. So what is the tonic measurement? Well, there are long-term changes in the skin conductance that are not directly tied to specific events. For example, we can measure the skin conductance level, which is the average conductance over a period of time. There's also the number of non-specific fluctuation, the number of random increase in conductance above a certain threshold. So these two can be measured over a duration of any stimuli, a continuous stimuli, and we can report the tonic value. But for research, we need to report more specifically the phasic measurement. The phasic measurements are short-term changes related specifically to an event or stimuli. That's why we will need those markers to know specifically the time windows in which we will want to analyze specifically what happens after a stimulus presentation, for example. The most common phasic measure of skin is the skin conductance response amplitude, SCR. And this refers to the difference between the peak conductance after a stimulus and the baseline level we had just prior to the stimulus. At our lab, we define skin conductance response as an increase of at least a minimal threshold in microsiemens, for example, 0.05 microsiemens, occurring within a time window of, let's say, 5 seconds after a stimulus. The amplitude of this response is measured from the baseline or the lowest points in the response to the peak. This type of measurement is useful for studying how participants process and evaluate a stimuli. Well, based on that, we are now ready. Let's move to the experiment where we'll go in two phases. We'll first start with a continuous stimuli presentation, in which we will add some manual markers, and a stimuli that we'll create in a timeline, specifically in Co-Lab. We'll create a stimuli presentation where we will have segments of this video.